So thanks very much, and yeah, thanks to all of the program committee, and especially thank you for the possibility of presenting online. I think it's great that conferences are happening in person, but it's also really great to be able to join from Europe. So this is joint work with Guillaume, Chapuy, and Baptiste, Louf, and it's, as the title mentions, about random partitions under new measures that we call Plancherel-Hurwitz measures, and they're motivated by high genus regimes for, on the one hand, maps, and for another hand, for Hurwitz numbers. So, yeah. So, as mentioned, we're talking about random integer partitions. So, partitions, I think, don't need to be defined, but I'll do it anyway. Are weakly increasing sequences of positive whole numbers. And we tend to represent them with Young diagrams. And the French convention, we put a row of boxes with the first part on the bottom, and then stack rows of boxes numbered with each subsequent part and line them to the left, and to represent a partition kind of graphically. And when it comes to studying random partitions, perhaps the most natural measure comes from studying random permutations. So if we take a permutation of the numbers 1 to n, choose it uniformly at random, a particularly useful tool for studying the structure of its monotone subsequences is a natural model of random partitions. So thanks to a purely combinatorial bijection between permutations and pairs of standard Young tableau, so ways of filling in the Young diagrams of some partition, the same partition with numbers so that they're increasing along both columns and rows. We can kind of extract the length of the longest increasing subsequence of a partition directly. So if we if we use this bijection, we sample partitions whose shape will be a given, sample permutations whose shape under the Robinson-Chenstead bijection will be some partition lambda. And this will define for us a law on partitions where we just have the number of standard Young tableau, we denote that f lambda here, squared, to count the fact that we're counting pairs as a weight, and then we have a normalization for the number of permutations and factorial. And under this law, we have something that's particularly useful for studying the statistics of this first part, because here, when we look at the statistics of the first part, we're looking at the statistics of the longest increasing subsequence of a uniform random permutation. So that's the kind of most classic case of studying random partitions. And this is something we're going to generalize through another model of non-uniform elements of the symmetric group, in particular factorizations by transpositions. So I'll introduce this first and then talk about how this particular generalization of the Plancherel measure appears in other contexts, because I think we're the first person to give it a name, but not the first person to study it by any means. Before talking about the regime that we're interested in and how that relates to combinatorics of maps, which have been introduced, I think, in various talks today. In particular, how we can use this as an approach to look at a high genus regime for maps, which is particularly difficult to study with other techniques that have received that. So to introduce this other situation where we're using partitions to study elements of symmetric groups, we consider is a transposition factorization of the identity. So take some symmetric group of order n, and we'll find L, a number L of transposition, so exchanges of two elements, such that their product gives you the identity. And if we count the number of ways of doing this on symmetric group of order n with L transpositions, so it'll give us a classical Hurwitz number, which has a meaning, profound meanings in numerative geometry. But first, we're interested in just a definition in terms of number of transpositions. And we won't require that the factorization of transpositions will be connected. So call these unconnected Hurwitz numbers for simplicity. And once we don't require that they're connected, we have through some nice algebraic identities, we have an expression for these numbers as a sum over the irreducible representations of the symmetric group. So in particular, by Frobenius's formula, we can express the number of transposition factorizations as just the sum of the dimension of each representation squared by these normalized characters here to the power of L. Normalized characters of a transposition on each irreducible representation. But because we're talking about the symmetric group, the irreducible representations are just indexed by partitions. So for order n, they're indexed by partitions of n. And in fact, the dimension of these representations and the normalized characters are just data that we can read off the Young diagrams of the corresponding partitions. In particular, the dimension of the representation is just the f lambda, the same number of standard adjunctive below that appears via the Robinson-Schenstock algorithm. And then the normalized characters are just the sums of contents. So the contents of a box of a Young diagram is just kind of a measure of how far that box is from this main diagonal here. So here's an example where it's filled in, and here the content sum would just be 3 because the other terms cancel each other out. And from this, we get a definition. I'm not sure if the controls from Zoom block part of my screen. With me, they do. Hopefully not. But
what's happening? You need to try to do something.
Sorry, I thought I have a kind of control panel from Zoom that I moved, which hopefully was never blocking anything. So sorry.
No, it looks great. You're fine.
Okay, great. Thanks. So now that we have something that's for any even number L, we're talking about a positive whole number, which means that for any positive integer n and any positive even integer L, we can just reinterpret this as partition function of some measure on partitions. So just dividing by our HNL, we'll take this as a definition for what we call the Plancherel-Hurwitz measure. So there should be a square here, but this is so something that is a natural generalization of Plancherel measure. We see if we set L to 0, we're counting something trivial, just the numbers of factorizations by 0 transpositions, but we recover the classical Plancherel measure. And what we look at is a regime where L is no longer 0. In fact, it's not finite at all. It grows linearly with the order of the symmetric group. And we will call this, for reasons that I'll explain, a high genus regime. And what's interesting is we can find quite a novel limit shape behavior for random partitions in the large n limit here. So in particular, we find is there's kind of a 2-phase limit shape. We have one part, the first part grows very, very large, grows with n over log n, while the rest of it behaves like you would see a partition behave under the Plancherel measure. So we have the first part and the length, which are equivalent to 2 root n, and the rest of the partition has a limit shape which converges in probability to a smooth curve bound by Verschuren from Chat. So these are the final of the way, but just to show how different behavior you can get in this kind of regime where L grows linearly with n. This is a sketch of the behavior, which some part might be familiar, but the first part does something very different. And from this also lets us get back as a kind of result of the limit shape theorem we have. We also have an asymptotic estimate for the numbers H and L, the unconnected Hurwitz numbers, up to exponent of little of n, so up to polynomial corrections. We know what these numbers look like. So now to talk about where exactly the same measure has appeared in different contexts. The first place is in connection with integrable hierarchies. So this was proven by Openkopf in 2000 that the generating function, exactly for exactly these unconnected Hurwitz numbers, is a tau function for the Toto equation. And this was then used by people in combinatorics, Yang and Zagier, to find a recurrence condition for the connected part of the Hurwitz numbers. So connected Hurwitz numbers would count factorizations by transposition where we require the factorization to be transitive. And what's interesting here is that the expression used by Openkopf is exactly the one we have from Frobenius's theorem as a sum over integers through representation theory. And the reason for that is that integers map very directly to fermion configurations, which kind of give a natural integrable structure. So a comment at the start of Openkopf's paper is that the generating function of double Hurwitz numbers can be recognized as a matrix element in infinite wedge space, some kind of natural anti-commuting space from mathematical physics. And you almost naturally have a connection to integrable hierarchies, or almost automatically have a connection to integrable hierarchies as soon as you have such an expression. So this uses a math that comes most easily from just taking the Young diagram of a partition, rotating it by 45 degrees and reading off the parts where the slopes are of the upper edge are negative. This will give you what we call a fermion configuration or Maya diagram. And on these Maya diagrams, we can express quantities in terms of anti-commuting operators, which give an algebraic way to find expressions directly. And one element, so the number of standard Young tableau, F lambda, is something that's quite easy to access via these anti-commuting operators. This is done by various authors in the early 2000s. And equally, the content sum is maybe less familiar, but is also something we can access with these anti-commuting fermion operators. But whereas in the case where you only have the F lambda, only have the number of standard Young tableau, which was treated by Johansson as well as Borodin, Openkopf, and Olshansky. In that case, you can use the algebraic structure of the anti-commuting operators to directly study every part of the measure, and you can find every correlation function explicitly and find some asymptotics that way, because we have a generating function explicitly for the determinantal point process. So here we know from the structure, because we have fermionic bilinear operators, we know we have some form of determinantal point process, but we don't yet have access to a generating function for the kernel. So what we're doing instead is we're using more approximate methods to let L grow with N. And what we have, which applies here, is an earlier result from the 1970s, which is independently found by Versching and Kirov, as well as Logan and Shep, where they were able to find the limiting behavior of a random partition under the Plancherel measure using the Hopland formula. So a formula for this number of standard Young tableau expressed in terms of these distances from each, as a product of distances from each square in the Young diagram out to the edge this way. And what they realized that you could turn this into a functional analysis optimization problem by writing this Hooke integral using exactly the same representation as you'd use to find a fermionic configuration, a tilted Young diagram, or a Young diagram Russian convention. then you can describe this outer edge by a profile, which we call psi lambda. We can kind of write explicit terms this way. And this is just a piecewise linear function. And in fact, we can write the Plancherel measure as an integral over these functions and solve this optimization problem to find the limit shape this way. And the main result is this convergence in probability of this outer edge in rescaled coordinates to a smooth function omega. And furthermore, there's an additional result, which is that although this convergence is in the rim subnorm, so it's not sensitive to what's happening on the edge here, they can additionally consider something like a growth process on permutations, which lets you see that actually there's strict bounds on the first part and on the length. So there's kind of a two steps to understanding the full limit shape, since we don't have bounds either side otherwise for the length and for the first part. So now to go away from the purely Plancherel case and see how we can get to finite L and later to L that grows with N. You can consider another case where our measure has showed up, and this is in a case of random walks on the symmetric group of order N. So if we consider a transposition random walk, so we start with, say, the identity on Sn, and then pick a transposition at random, and for L steps, act with a random transposition. We can ask some questions about the resulting walk, and one that Genus and Chapuy studied for this walk was how fast does the number of steps have to grow with the order of the group, so that in the limit as n goes to infinity, so as the size of the group goes to infinity, the permutation you sample after L steps is close to being uniformly random. And what they found was that there's a cutoff. So if L grows faster than half n log n, you have, after L steps, if n's large enough, you have almost a uniform random permutation. And that has a natural interpretation in terms of our counting of unconnected transposition factorizations. We can say, okay, if L is growing at least this fast, then we have an approximation, because the chances that we'll hit we'll hit the identity after L steps is just 1 over n factorial, or equal chances. And the number of steps to get there is n choose 2 to the power of L. So from that, we have an estimate for the numbers we were originally interested in, but also their proof along the way uses exactly this measure. It comes about through a kind of Fourier transposition onto the representations of this group. And what they find is that the only contribution that you need to consider in this case is from one partition. It's from a kind of trivial partition with all of the mass in one part. And we have a symmetry either way. It doesn't matter if we conjugate the partition, but it can be either just the first part or all just n parts, each one box in size. And just looking, we can see right away that just inserting this one partition into the formula kind of gives a good estimate, gives the same estimate that they already had back. So now I'd like to motivate the regime that we looked at, which, as I mentioned before, is linear in n. So it's somewhere between the classical Plancherel case and the case that's explained by the Genus and Chapuy result. And the motivation comes from somewhere else. It comes from combinatorial maps. So these are interesting to different people for different reasons that I think are probably have been motivated in the last few days and will be as well. But just to define them quickly, they're graphs embedded on surfaces. So graphs with some additional constraints, that we have a a fixed orientation of edges around each vertex. So for instance, we consider these are all equivalent graphs, but they're also equivalent maps. But here we've taken the same graph and we've got a different map by exchanging two of the edges. And here as well, these two different maps of the same graph are drawn on different surfaces. So the one on the left is drawn on a sphere, and the one on the right needs to be drawn on a torus. We need to punch a hole in the thing we're drawing it on in order to draw this map. And this is something we can read off the data of the map using the Euler characteristic relation. So for a map, we can draw it on a surface of genus G, so with G holes in it. If there are 2 minus 2G vertices minus edges plus faces. So that's kind of the rule. And the reason we're interested in this in the context of transposition factorizations is that there's a way of constructing a map related to each transposition factorization. So here we just take, if we're on the symmetric group of order n, we'll take n vertices, label them 1 to n, and then the L transpositions we consider, we kind of label them and have them as edges, and depending on the order of the transpositions, we'll join up the vertices which are the labels in each one of the transpositions. So here's an example of how the procedure can work for factorization 1, 2, 2, 3, 3, 4, 3, 4, 2, 3, 1, 2. So this is on S4 with 6 transpositions, and we can, since we don't necessarily have transitive factorization, we don't necessarily have connected maps. So for instance, here if we have a connected map, in this case, we necessarily are on something with genus 0. Here we can have something genus 0 plus something with genus 1. Here, 2 things of genus 0 plus something of genus 2, because actually we should be looking not quite at the genus and the Euler characteristic relation, but the sum of genera. And this construction appears in the literature more to do with constellations, so a more general object that has kind of natural encoding to do with permutations, and uses more generalized edges called hyperedges. So in this one special case where the permutations including a constellation are all transpositions, we have a map rather than the more general object constellation. And in where these have appeared in literature, most notably studied by Busquets-Mourou and Scheffer, as well as by Duki, Pourhan, and Scheffer, they've this construction has been shown to be part of the universality class of maps. So maps have these kind of universal enumeration in the planar case, as well as a universal scaling limit, which is strongly conjectured for these Hurwitz maps as well. But why we were interested in this in the context of partition is our model of partitions is that we have a way of quite easily treating a genus that grows along with the size of the map. So the high genus case for maps is particularly hard to treat. Only one serious advance has been made recently by Thomas Baptiste and Baptiste Louf, where they treated high genus triangulations, and from that they were able to get the first numerical or first enumerative estimates for the number of such maps, which is also to e to the little o of n, in a case where the genus grows linearly with the number of vertices. So this was the regime that we were interested in, and for that reason we looked at L growing linearly with n, which through the Euler characteristic relation means that the genus is also growing linearly with n. So we're somewhere between the two regimes, given on the one hand by the Plancherel measure, the other hand by the almost random shuttling case of the Diaconis and Shashahani measure. And our main result is that we have some kind of mixing of these two shapes. So we find that the content sum wants to just come from the first part, and that should be of order 2L to the 2L over log n, while the rest of the partition just tries to optimize the Plancherel measure part. So now the little time I have left to recall what this looks like, I just briefly like to say what our proof looks like. Really, because we have this sort of 2-scale limit shape, we have a sort of 2-scale proof. First, we have kind of macroscopic properties that will have an exponential cost if they're not satisfied. We find first that only the first part needs to be bigger than some threshold, say n to the 1 minus 1 over 100. And then we have an optimization problem for that, as well as the optimization problem that you'd have under the Plancherel measure. And along the way here, we actually show in comparison with enumeration of partitions exactly what the enumeration should be up to e to the little o of n. And then we have some refinement afterwards in order to show that the length and the second part are bounded by 2 to the root n. So finally, just to come back to the map picture, what we had been interested in was trying to compare with the results for connected maps, so the more interesting combinatorial case. And unfortunately, while we do have this numerical estimate that's e to the little of n, it's the same level actually as Budzinski and Louf's estimate, what we find is that the objects we're counting with high probability are not connected. So we have all of the edges of the maps and all of the genus going to one component, but it doesn't have a large number of vertices. It has big O n over log n vertices. And just to conclude, so this generalization led to some interesting generalization of the limiting behavior for partitions, kind of a mixing between the Genus and Shashahani case and the classical Plancherel case. And there's a lot of other questions that remain open. So I'll stop there, and thanks for your attention.
Harriet, we don't see you anymore, so you're in the dark.
Oh, apologies. I hadn't noticed.
Sunset there, right?
I guess this is the issue with the time zone change. I hadn't noticed.
That's better. Any question in the room?
Yeah, I should find a light as well.
There's a question by Marie.
Hi, Annette. This is Michael. I have a question actually related to the first open questions concerning like different other scales of like when n is equal to square root of n. You mentioned where by Christian. Like, is there a limit shape? Is the limit shape the same? Is there some
so just check, the question is the intermediate regime for n, something like n to the, I didn't hear properly, sorry. So this reference to Vian, he hasn't exactly studied this measure. It should be related to the measure he studied should be related to ours, where L has been Poissonized in some way, and actually the limit shapes found in his paper look quite different to ours. So we haven't really managed to understand that connection, but we think that this kind of threshold, heuristically, it should be interesting because you kind of have a similar level of contribution from the Plancherel part as the first part, if that makes sense. And we don't know much more other than we know above a certain point, yeah, you should have a large first part. That's
Other question? No. Is there any question?
Yeah, how about questions online?
No question on the line? Okay, so then thank you again.
Thank you.